Assalamualaikum, bismillahirrahmanirrahim. Hello everyone. So we have finished in our last video at chapter number 9, talking about relief valves and the types and the scenarios and so on. So what we are going to do now, we are going to try to solve some problems in chapter number 9. Well, chapter number 9 doesn't have a lot of calculations. It's more about now understanding and using your knowledge of the industry and what a pump, if it is blocked, what could happen. So it's more qualitative now rather than quantitating things together. So what we are going to do now, so we have problem number 99, and it's talking about determine the location for the relief valves, where we can have relief valves. If you look at it, we need to understand the process before we say we can talk about the location of the relief valves. So if I pump here and my pump is pumping crude oil, and as it's pumping crude oil to the fractionation units, then we have it is heated up. It is heated up, as you can see. You see the steam here? It is heated up. And how to maintain the temperature? We can maintain the temperature of what is entering here to this distillation column or the fractionation unit. We can do this by what? By controlling, you can see the temperature controller. By controlling what? By controlling, let me enlarge this a little bit. By controlling the flow rate of the steam, So we increase the steam if we want higher temperature. We decrease the steam if we want lower temperature. It depends on the set point that we have identified for the temperature controller. So it enters here. After it enters, we have already nitrogen purgings for inerting and whatever. So this is like what's happening in the distillation column. And of course you have the distillate going up and you're trying to cool it down, and you have a controller here to make sure that you have cooling water. You see the cooling water here, so that it's cooled down and it's collected in the drum, and we are taking some kind of methanol or whatever it could be. Okay, and of course we're going to have from the bottoms, we are going to have a pump that will pump our tars. Okay, the very heavy tars here. And of course what they are using, before you send that to tars, what happens here is that the reboiler section, where you put steam in and you try to reboil this vessel, to reboil the bottom, so back into the distillation column, so you can have more separation and hence more distillate and more tars. Okay, so where are the areas? Where are the areas that we can have our relief valves? Where I could have a blockage here, right? So I can have a relief valve standing up here. I could have a blockage here, so a relief valve also here. And when I say relief valve, both of them are liquid here. So remember we said safety valve, relief valve, and the safety relief valve. Can you recall this? So what we have here actually is we add a relief valve. A relief, that means it's for liquid. So that will be, sorry for that. So I just choose my, okay. So I'm going to have something like that, and this is my valve. I know this is the spring. Come on, spring. Okay, so that is my valve here. And what else? I'm going to have it here as well. I'm going to have it here, and on the discharge, right? We always say that we want it on the discharge. And what else? You can have it. So here we are having like two vessels, we have two discharge pumps that we want to keep a relief. Where else do we have? You can see that I'm having cooling water here that is trying to cool up my system. Imagine that this is not cooling. Oh my god. So it could cause a problem here, that there's an expansion of what is getting inside. There's an expansion of heat because it's not really cooling down enough. So I can put a relief valve here as well. And what else can you have a relief valve as well? You have the distillation column, you have the vessels. All the vessels can have relief valves. And actually here you can, we don't know what's the, it's just methanol, it's not that corrosive, but I mean, if you want to, you can add that rupture disc, and then you're going to add the other valve here, okay, the spring valve. You also can add here, so here we have liquid and gas, so it's a safety relief valve. The type is a safety relief valve, and we are going to have our spring valve here as well. So all the vessels, even here, and we are going to have also, what did I say? I said that we can have it here. What else do you can guess to have? So we also have a steam line, right? Steam line. Imagine that we have on the steam line the low pressure steam developing via regulator from higher pressure steam, and you're having like the steam here is just producing more and more heat, and it never stops, okay, and it's heating up the system, considering other things that are totally normal. So I could have some problem also with on the steam line having a higher pressure coming in, and having a higher pressure coming in, so I can put also a relief valve that could be here, okay, that could be here. So you can see that I'm adding my relief valves all over the place, the places that I think that I have overpressure. And then I can talk about scenarios. Scenarios like if this goes off, right? If this goes off, there's nothing going in. What will happen here as well? There's no crude in, so mainly the temperature will drop down, which is okay now in this case. But you need to take scenarios like what will happen to this pump to protect it, and what will happen to this vessel, and to make sure that if there are any products will be affected to protect it. So that is the idea. Now let's go to figure 9.15. In figure 9.15 we have something really different. We have two vessels, polymer vessels, and we have the steam getting in, and we are trying to control the temperature, and this is the controller that I have trying to control my liquid inside here. And then I have a pump that pumps to a centrifugal pump that pushes it to the polymer storage and to the Hickson storage, because I have one and I have two different products. So what I have relief locations, I have a relief location on this vessel and also on that vessel, and I also will have on my cooling system. I'm trying to cool up the system here, so I'm having on the cooling water line between the exchangers, right? So somewhere here, and I also have steam lines next to the vessels, and my steam lines, one is here and the other one is here. So I also need to make sure that I don't get a high pressure system from the steam. So I need on the steam line to put a relief valve, and that as well. So this is generically of how to deal with things in this kind. I already talked about some times, but if you want to talk about the same problem to determine what types of relief valves should be used at each location. So going back here, so what type of relief valves should I use? Well, if here it's a liquid, right? So a relief valve, definitely. And here's a liquid relief valve, definitely. Here we have both, so we can use combined. So it would be the safety relief valve, right? And for the steam, it could be a safety valve, definitely. And for the vessel here, for the separation that I have here, I'm going to use the rupture disc, and then I'm going to also use the spring safety valve as well. And if I'm worried about that I'll get a backup pressure from here, I'm going to use the below one, the bellow, which is also has spring, but it's a bellow one, balanced one from the backup pressure. So here I'm just identifying the types of valves, relief valves that I will have here. I did not draw here what are where I can keep, just a quick one here and here and here and here as well. What else? I'm going to put it here, okay, and here. Okay, so I just included that in every location that I would expect to have an overpressure. And talking about the two vessels here, I'm going to use again a rupture disc and then a spring or a bellow one to also protect me from the backup pressure. And the rupture disc makes sure that anything in contact with this corrosive material would not affect my spring one. What about the ones on the steamed ones? The steamed, they're going to be safety valves, only gas, and the one on the liquid stream here is going to be a relief valve because it's for liquid. So and here also to be for liquid service. Okay, so these are the questions that we cover for 9, 11, and 9, 12. And now the question is asking us, well, again, we go back and say, what are the recommendations for the total contaminant systems? And we already talked about the total total containment systems. And we said that if you want to contain that system, we use a scrubber to collect, or just like an absorber, something like that, after the knockout down the drum. So the containment system, it depends that if it is flammable or toxic. So it's non-flammable, non-toxic, and which is the normal case, we vent to the atmosphere. So here we say that the general case that if it is non-flammable, this is written in the PowerPoint slides, by the way. If it's non-flammable, non-toxic, toxic, and it's not really infrequently. I would say that it's not always that you're opening that continuously to the atmosphere. So it's infrequently vented. So here I would say that what will happen? We vent to atmosphere. We vent to the atmosphere. So here we are saying that there is a rule, generic rule here. But however, if it's flammable or toxic, that means we need a containment system like a catch tank. Okay, so then we need a catch tank or a knockdown tank, and then I will need a scrubber before going to flare, right? Just to make sure that we get the liquid out and make sure that we absorb any harmful thing, and then we just take it to the atmosphere, just considering that everything goes to atmosphere is safe and it is according to the regulations. What about if I have something else? Yes, I have the water relief and the steam relief, because I'm relieving here some water, I'm relieving here some some steam, and I'm relieving some water here, and this will just go finally to the ground. I mean, there's nothing harmful of putting steam, but to the ground and not to the not to the sea, where steam could kill some fish directly in direct contact with that. Okay, so these were the details that I have for here. What else? Well, what we have is that it's talking about here in 9:15 about the relief scenarios. Here are the relief scenarios. So what relief scenarios we have for the device? And the relief scenarios, I already mentioned some ideas. But if you want to go back to 9.9 and 9.11, so that is 9.9, what are the relief scenarios that we have? The relief scenario, first relief scenario, for example, that we have the size relief for pump on, that it is blocked, then that is blocked, and of course we need to put this on and this on, this relief valve if it is blocked. What about some other conditions? For example, the cooling coil that we are using, and actually it's not here. you're using some cooling here of water. So what about the cooling water if it is shut down? Okay, if it's shut down, that means that the temperature is going to be increasing. That could be dangerous. Even here that we have, where is the cooling here? The cooling, we have it, I think this is only for a drum. Yep, it's here. I was searching for it. So if you have like here the cooling, if it shuts down, that means this is going to be much higher on temperature. And being higher on temperature, that could be like less liquid and a lot of gases, and it's over pressurizing, and then we open that as well. We already mentioned that, but we are just mentioning like scenarios, right? We're trying to explain and get what scenarios that we can have here. Scenario could be, for example, that you have all feed in with a certain temperature, getting the distillation column, everything is good with the boiler heating and getting in back, and everything is good, and we don't have a reflux. Usually we have a reflux, yeah. So if the water fails to cool and then we have a reflux, so you're also adding heat. Imagine that this is blocked. I am just putting worst scenario case. That means you're going to have build-up of temperature here. So if you have build-up of temperature, and so the worst case scenario, you will still have this working system here. So we always go to the worst case scenario just to make sure that if things are going to go well, and we can relieve that overpressure and not to cause any explosion. One of the actions that we could expect that if you have steam here that is very high pressure due to a certain reason, this is fully opened and it's getting ill, and will this pipe be able to withstand that steam? We already have a relief here, but you're saying that will it be able to withstand this or not? So sometimes it's also important to know that, because we also want to protect the pipe, which is part of this whole system here. What about if I have my inerting thing, or the purging that I'm doing with nitrogen here also does not work? So that is something else that I could have some kind of flammability limits here, and getting flammability limits could also be dangerous as well. And again, anything that can be blocked. So this water being blocked, the steam being blocked, or that pump being blocked, this could be being blocked. Here the methanol, sending to storage is blocked, so there's nothing sending and it's just collecting up within the drum. All these possibilities for getting a very high pressure and should be considered. Beautiful. So these were the main questions that I would like to cover in chapter 9. Well, in 9.17 it says develop sketches of reactor vent system for the following 4 cases, and maybe I'll not do the sketch. I'm just thinking of doing the sketch or not, but we have cases here where the reactor relief is vapor only and they are toxic, and the relief vapors are high boilers. As we have only vapor only, I can guess that I would use, it says toxic. Well, a spring ones can also handle toxic, but I don't need a rupture disc here in this case, because I have vapor only. This is toxic, not corrosive, right? But if I would talk about, but I say that's toxic. If it's still toxic, a bit worried about it. So I think so we'll add better a rupture disc with the spring one. Okay, with a spring. It's all because of this toxic thing that makes me rethink about it. What about second B? We have contents also a corrosive. Again, I need to consider this, that I will have both rupture disc and the spring relief valve as well. Well, going to C, I have two-phase flow and vapors are low boilers. So in this case, that I think so it's fine to use only the spring one, because we don't have any toxic or corrosive stuff as well. and of course all of them will be going to what we're going before it goes to the flare. It needs to be treated within it goes to a knockout down vessel, and then it goes to the scrubber or flare or whatever to contain it. Okay, and the last case in which I have everything, definitely I'm going to have the what they call it, the rupture disc, and the spring one as well. And then of course it can be send it to flare or a scrubber. So these are the kind of things that you just get the idea of how we can deal with the things that we have here. And if you just want to have a look about it, it's good also to look. So that's 917. Okay. So 917, where we had in part A, where we had a vessel here, and in this vessel, what I'm trying to do, because I have only relief of vapors, so I have my rupture disc, and then I have my spring one as well. And of course, in this case, this is what we need to do. And of course, and then what you're going to do, you're going to send it to flare or to the scrubber. Okay, what about D? So, sorry for that. And in part B, what you have very similar case here, that you have something that looks like that. And again, because it's toxic, so I'm using a rupture disc, and then I'm using something like that. And this is like just a relief valve. This comes from the knockout. That comes from the knockout vessel that I have here. And of course, it then will go to the scrubber, where you are trying to contain it, or of course the flare. Okay, so this is like as we have explained. In part C, it's simpler because we have no toxic substances. So in this case, I will directly have this. I have only the spring one, and this everything is really contained in a knockout drum, and then of course it is taken to the scrubber or flare. Okay, and part D is very similarly done, that I have a system which looks like that, but because I have all of them, I'm going to have the rupture and the spring one, and of course with the scrubber and the flare. So this is what we have for 917. I think so that was like straightforward. Do we have what else do we have from questions? So in here, that is like, as you said, that is straightforward to do it, but it's fine to do it together. Determine the vapor velocity inside a horizontal knockout down for the following three systems. So we have three systems. It's enough to do now for one. So what do we have? We have a knockout down, and these are the information given to us. Rho V is equal to 0.03 pound per feet cube. Nu is equal to 0.01 centipoise. The rho L is equal to 64 pound per feet cube, and the diameter given to us is equal to 300 micrometers. Okay, I'm not sure if this is micrometers or microfeet. Let me check. So it's micrometers. Okay, micrometers. So these are the information that we have. Recall what we need to do. We have the equation for UD. That is the drop-off velocity, which is equal to 1.15 into GdP rho L minus rho V divided by rho V into C. Okay, so you can already see that I have that, and that, and that. The only thing that I don't have is the C. And where do I get C from? You get it from the figure and the equation. And that is from the equation equation that is equal to, that's a long one, that is the equation which is equal to 0.95 into 10 to the power 8 into cp square, that's the centipoise, right? Square. This is confusing because I'm putting the units, right? But you need to consider the units. I mean, I took it off, but you should be careful. Rho L minus rho V divided by mu square, okay? So this is what we have as an equation, and all what you need is just substitute and doing your conversion, and you're going to find that this is equal to 1.74 into 2 to the power 3, and this is unitless. And after you get that from the figure, and this is the figure that we have, and as we have 1.74 into 10 to the power 3, which is 1743, with somewhere here, it looks like it is like 2, okay? The drag coefficient is equal to 2, and here from figure, we said like from figure 9.13, I have C is equal to 2, and then I'm going to substitute now into the equation of UD, the draw up velocity, which is equal to 1.15 into the all the bits and pieces that I want to include in my equation here, 63.97 over 0.03 into that discharge coefficient, which was 2. And doing this, you're going to find that the drop up velocity is equal to 6.68 feet per second. Now you can do the rest for B, C, and D. Okay, so that was the problem. For calculating. I think we were here. Yep. So we finished the part where we are talking about how to calculate the drop of velocity, the vapor velocity inside this knockout drum. Great. So 919 talking about the height of the flare, if you want to calculate the height of the flare. And again, it's just an equation that you're going to substitute. And we have the vapor flow, which is the mass flow, molecular weight, heat intensity, the Q, the distance in which we're getting this heat intensity, and the stack diameter. And it's important always to know the height of the flare, but it's also important to know the vapor flow, so that we can have the equation on the other way around. Now, doing so, 919, we already have our requirements, or all the details that we need. So the equation 9.4, that's equation 9.4, where we said that HF is equal to minus 60 dF plus 0.5 into 120 dF square minus 4 pi QF into XF, which is the distance, okay, minus 960 QM, the mass flow rate, into the square root of mass, molecular mass, divided by pi QF. And in doing so, and doing your substitution here, you're going to get the answer as equal to, for case A, because we have 4 cases, HF is equal to minus 120 plus 0.5 into 328, which will be 44 feet. Okay, so that is the height, and so it's just a direct calculation that you're going to do here. Okay, just make sure that your units are always right, because it's always the key of the units that someone could make mistakes here and there. Especially, let me make sure. So here we have BTU per hour feet square, and here we have pound per hour feet. I think so. Things look great for me. I think things really look great for me, and everything seems really fine to just substitute. Okay, so that was the problem that we have solved for 919. Now finally, the last question that I would like to cover in this chapter here is this problem here, 931. 931, what it says, identify the problems with the relief valve configurations shown in figure 916, and this is 916 in front of us, and it's asking us, please tell us what are things going wrong, what is going wrong in this, and these relief valves, how they are installed, okay, how are they installed here, and what was wrong with them. So the first one is A. Now we are going to start with A. And in A, what do you think there's a problem with? So we have the vessel, and out of the vessel, we have a rupture disc, and then we have this valve, and then we have a we have a spring valve opening. So what do you think that went wrong there? Okay, so the thing which really we have wrong is this thing here. We cannot have, or we cannot allow a valve that blocks a relief. So it is not allowed to have a valve that blocks a relief. Okay, so that is the thing that we need to be careful about, and that should not happen. What about B? Do you think there is a problem with B or not? Again, it's the same story. I have a rupture disc, which is a relief, and this is just coming on the way. It could, imagine it, just think about it, right? You're having a relief valve, and this rupture, he killed himself. He broke into pieces that disc just to make sure that this place is safe, and then this valve accidentally it was blocked or closed. Imagine, right? This is open and this is closed. Oh my God, right? So it shouldn't be like that at all. And so great. So what about C? What is the problem of C? So it looks like what we have is here is like an inlet or whatever, inlet or an outline. It applies the same, but we have an inlet line here. Inlet to a vessel. Can you have a relief valve on an inlet for a vessel? No. This valve should be sitting at the top. It should be sitting at the top. Okay. We shouldn't have it on the ledge. Like it should not be on the inlet or outlet of a vessel. Okay. Inlet or outlet of a vessel. So that was part C. What about now part B? Okay, yep, think about it. Okay, so what do we have here? So we have, for example, there was a lot of gases here, and now there was a high pressure, and then it goes like that. What happened here is that I have a valve that blocks to my relief valve. So any prevention of block, that is a problem. So we have a problem here that is related to that relief valve, and instead this relief valve should be sitting here, and I have another one here. The other thing that I can see, this is a corrosive liquid, and since it's a corrosive liquid, you need to put a rupture disc here before it goes to the spring one, so it becomes in series with it. Okay, so that is for part D. Why are we doing this? Again, this is much cheaper. Let the disc be in contact with the corrosive liquid, and we can replace it from time to time. But if we keep this in contact with the spring one, this will kill the spring valve that we have, relief valve, and that could be a problem, or it could be very expensive as well. Okay, what about E? What about E? So we have, look at it, we have supply tanks, enclosed, open, and then we have the relief size for the two tanks. Okay, this is the relief size for two tanks. So what's the problem do you think that we have here? The thing that I can see here is that this was designed only for these two, to relieve for the two tanks, right? The worst case scenario that all of them are supplying, it happened that this is open, and that is open as well. Will that be able to withstand all that pressure that is coming up from all the three or not? So you see, like, we are going to the worst case scenario, that all of them are open, because we always want to make sure that our plant is safe. Okay, so that was part E. Now let's go to part F. In part F, it looks like it's fine. What about this inches, 1 inch and 2 inch? Does it click into your mind about something? The thing that you can see here is that this pipe, which is 2-inch pipe, and the discharge pipe here for this valve, or the discharge line, is 1 inch diameter. And actually this is the problem, that what we have here. The discharge pipe must be larger than the inlet one. Okay, the discharge will be greater than the inlet. Okay, what about G? What about G? What do you think? That we have a problem? We have a rupture disc here, and we have a spring one here. Can they be like that? Well, what is the problem here? We said that could be one of the installations. If you can recall, that we had our system here, and we said that, well, you can have something that looks like that. So rupture disc and spring loaded relief. Normal relief may go through spring loaded device, and rupture disc is back up for larger relief. So that the rupture disc is back up for larger reliefs. So you can see that we said that the rupture disc should be a backup. So the pressure for the rupture disc it is at a higher setup pressure. So what is the problem that we could have here? And the thing that what we had here in part G is that this will go out first, and then of course the rupture disc for backup. But the problem is that you can see how close are they, and they are only about 10% difference, which means that even if this goes back to setup pressure, or when it goes about 100, it goes 100, but still it goes higher, even though that this is open for some time, and this would affect the rupture disc, which may not operate at the correct pressure because they are very close to each other. Okay, so this may not be operating at the correct setup pressure. Moreover, that if I have, for example, something like here that is corrosive or liquid, for say, like let's say like a polymer, and it goes out here, and imagine that it goes out on a line, and then it goes, some of it goes entering this rupture disc, and it damages it, right? And so there is something that could close, that it closes this plug of this rupture disc that we have. What about H? What is the problem? So we have a polymer here, and we have terminated pipe. I may have given a hint about polymer that they may plug or block things. And so what do we have here? So we have a polymer, and this polymer that we have, it may cause the blockage of this. So we should be careful when we use a spring one, and when it is getting attached to some liquids that could be plugged with polymer. Finally, we have we have this kind of a system, relief system. We have a spring one, and this is what I have here. So what is the problem that we can say about this system here? The problem that we have here is that we have a relief here, right? We have a relief here, and what happened? This is like a true case. Is that they were worried about that if it rains, and it's raining all the time in that area, and that it always comes inside this valve, relief valve, and it blocks it. Okay, so what did they have done? They put a roof. And actually, when they put the roof, when this relieved once, it caused a big hole here in the roof. and by the way, what is the best solution for that? Well, keep anything that could block up, like any cup. Like, I don't mean a cup, but it's like a cup just to cover it. And when it blows, let it blow this cup away, right? But we don't want to have holes in the roof, which could be like causing a real problem. So that instead of blasting a hole in the roof, which had happened, we maybe only use like a cartoon cut equivalent to that place of the valve here. Okay, so something like that. And then you put just a cup over it. Okay, now going to part J. Part J, it gives you some kind of information here, more than as usual. We have 100 gallons per minute pump, and we have also another 100 gallons minute pump, and then we have output 100 gallons per minute, and the relief size is also for 100 gallons per minute. Does that sound good for you or not? So if you do your math correctly, you're going to see that this is size for 100 gallons only per minute, and actually what do I have? I have 200 in. But you're going to tell me, well, I'm getting 100 out. Well, I could tell you that there could be a blockage of this 100, right? And then I have 200 in. So this relief should be able to get my 200, which is in, out, rather than this vessel blasting, because it has no more space. Like, you're relieving, but you're having more in because this pump is blocked. So that's the idea. Taking the worst case scenario, you need to size this to what? To 200 gallons per minute. Okay, so these are the wrong things, I would say, that is in this, and it's all about sizing. And actually, that is the end of our problems in chapter number 9. I hope that you gained a lot. And what is left? What is left in our next video? We're going to cover the hazard study, the risk assessment, with the what if checklists, and other types of checklists. All this will be part of chapter 10 and 11. I'm going to get bits and pieces from here and there. We're not going to cover each piece, but we're going to give you a good coverage of that in our next video. Till then, thank you very much. I appreciate your presence and your listening. Masa.